It's time to get your arrows popping.
Ladies and gentlemen, this is Mr. Whitt with Fort Bend Tutoring, and in today's tutorial we'll be discussing systems of equations with three variables. I know you can't wait to dig into this, but would you please go ahead and subscribe to our YouTube channel, Fort Bend Tutoring? I would greatly appreciate that, and go ahead and click on the notification bell because we're about to dig into systems of equations with three variables. So once again, you're already subscribing to the YouTube channel, Fort Bend Tutoring. Thank you. And we have before you systems with three variables. And I want to discuss the format of today's video. We will have 2 problems dealing with the substitution method, 3 problems dealing with the elimination method, and we have a bonus word problem all packed into today's video. Also notice that we have a new format, so give us some feedback on whether you prefer us capturing the screen as we're doing in this video versus how we film it with the camera where you can see my hand. Let's go ahead and move on into problem number 1, where you want to first of all identify the fact that this is ideal for the substitution method. Why? Because they've already solved one of the variables for you. You already know what z is, my friends. You know that z equals to 1, right? So let's just use this to solve the system of equations. So being as though I know that z is 1, I'm going to choose one of the other equations, either the first equation or the second equation, where I can plug in this value of z. So let's go ahead and start in order with the x variable. Yeah, I'm going to go in alphabetical order here in solving for my variables here. So we already have z, right? So I want to go with x and then I'm going to go with y. So that means that I'm going to take the second equation, this x minus 4z equals to -2, and I'm going to replace our value of z with 1, just like this. Yeah, just like this. That means that next I'll be multiplying -4 and 1 to get x minus 4 equals to -2. From here, I'll be adding 4 to both sides of the equation, like so. Our 4's will cancel out, and I'll be bringing down x equals to +2. So we want to hold on to this value because we now know that x equals to 2. In fact, we can go ahead and identify the fact that we know that z equals to 1, that we can identify that x equals to 2, and then move on to the first equation in order to solve for y. So when solving for y, we'll have y plus 2z. This equals to 3, right? And we were told this from the beginning, but now I'll be plugging in 1 in for z. So I have y plus 2 times 1. This equals to 3. Amen, amen. From here, I'll be multiplying that 2 times 1. And so I'll have y plus 2 equals 3, then subtracting 2 to both sides of the equation as we do. Our 2's will cancel out, and I'll be bringing down y equals to +1. Let's hold on to that. So we'll circle it here, and then we can write our solution as an ordered triple. Your ordered triple here then is going to be 2, 1, and 1. Knowing that the first value represents x, the second value represents y, and the third value represents z. So this is how you would write your solution as an ordered triple. Amen, amen. Red, box it. Just like that, people. Here I want to remind you to please donate to our YouTube channel. Our donation link is in the description box and on the About page. With these donations, it helps us to bring you more free math tutorials from me, Mr. Whitt, and Fort Bend Tutoring. So your help and your donations strongly influence how often and when we have videos available for you. Moving right along to problem number 2. Here we have a system of equations, and we'll be focusing in on the elimination method in this problem right here. Notice that it is only the second equation that has 2 variables instead of 3. So in the second equation, we have -x plus 3y equals -4. So what that means for me, that means I want to go ahead and group together the first and third equations, all right, with the focus of eliminating the z variable from these equations. Now the y am I choosing the z variable in order to eliminate? Because our second equation doesn't have the z variable. That's why. So that's why we're going to grab that first equation, the third equation, and we're going to use the elimination method to eliminate the z variables from these two equations that I've identified here. And in order to do that, I'm going to multiply the entire first equation by 3, whereas I'm going to be multiplying the second equation by -2. The reason for this is because I want to make additive inverses, aka opposites, on my z variables. If you focus on the z term 2z and the z term in the second equation 3z, the first common multiple that they have is 6z. So what I'm doing is I'm multiplying the entire equations based on that least common multiple for both 2z and 3z, which is 6z. If you want to check out a video on how to find the least common multiple between terms, check out our video called Finding the Least Common Multiple. We'll be putting a link right on your screen. All right. From here, we'll be distributing. So I'll be getting my arrows popping as I distribute that 3 to each and every term in the first equation, and then coming back and distributing that -2 to each and every term in the second equation in my new system here. Distributing, you'll end up with 3x minus 6y plus 6z equals 27. In the second equation, you'll have -4x plus 10y minus 6z equals to -32. And now we can eliminate the 6z's in our problem here. As you see, our 6z's will cancel out, and we'll be bringing down -x plus 4y equals -5. Just like that. And we want to hold on to this equation. So let's go ahead and identify that we're holding on to this equation here. And we want to hold on to the fact that that second equation is going to be used in conjunction with it. So with those two equations that we held on to that contain the x and y variable without the z variables, we're going to go ahead and continue with the elimination method by making opposites of the x terms. Now, you could have made opposites of the y terms as well, but it's going to be easier to make opposites of the x terms in this situation, being as though they have the same coefficient of -1. Because all we'll need to do is multiply one of the equations times -1 to make them opposites. And that's what we're going to do here. So once again, I'm going to get my arrows popping here, okay? And distribute that -1 to every term in the second equation. And that'll give us the following system. We'll have -x plus 3y equals -4. You'll also have, oh, that is an ugly 4. He can fix it though. Let's fix it. We'll have +x minus 4y equals +5, and then we'll combine these terms. So what happens is, all right, setting it up, your x's will cancel out. You'll be bringing down -y equals to 1, and then you'll be able to solve for y by dividing both sides by -1. So let's go ahead and do just that. Your negatives will cancel out. You'll have y equals -1, and this is your answer for y. So now we know that y equals to -1. Using one of the equations at the top of the page here, we can also solve for x. So let's do just that. Using the first equation, you can have -x plus 3 times -1 equals -4. So what I did was I took our first equation at the top of our page here, the -x plus 3y equals -4, and I replaced that y with our result of -1. Simplifying, you'll have -x minus 3 equals -4. I hate this equal sign. Let us fix it. Thank you. All right, a little better. No. There we go. A better equal sign. Now you'll go ahead and add 3 to both sides of your equation, like so. Your 3's will cancel out. We're bringing down -x equals to -1, then dividing both sides by -1. Your negatives will cancel out. And now we know that x equals to +1. Go ahead and hold on to that solution. So now that we know that y equals to -1, that x equals to +1, let's plug these values of y and x into one of the original equations. So I'm going to choose our first equation, which was x minus 2y plus 2z equals 9 in order to solve for z. We'll be replacing x with 1, then replacing y with negative 1, bringing down the positive 2z, which equals to 9, and then simplifying. We'll have 1 plus 2 plus 2z equals 9, then combining your like terms on the left side of the equation here. 1 plus 2 gives us 3 plus 2z equals to 9. Then we'll subtract 3 to both sides of our equation using the addition property of equality. Your 3's are going to cancel out, and we'll bring down 2z equals to 6. Now we'll divide both sides by 2. So here I have my 2 going into each side of the equation here, and the 2's cancel out on the left. We'll be bringing down z equals to positive 3 after dividing 6 and 2. This gives us our last solution for the 3 variables we were seeking to find. Writing your solution as an ordered triple, you'll have x being equal to 1, y being equal to negative 1, and z being equal to positive 3. So this is our solution as an ordered triple. Red, box it, just like that. All right, here we have example 3. With example 3, we're going to be using the substitution method. And once again, you're looking for an ideal when you're using substitution most of the time. For instance, I am recognizing the fact that in the third equation, it's going to be easy for me to isolate the variable x and find out what x is. So doing just that, we'll take this 3x, which equals to negative 15, and we can just go ahead in our first process of the problem and solve for x to get negative 5. Yeah, now we know what one of the variables equals to, right? Let's go ahead and hold on to the fact that x equals to negative 5. Using this value of negative 5 for x, we're going to plug this into the second equation. Why? Because in the second equation, you have 2 variables. And now you already know one of the 2. So it's going to be easy to solve for the second one. In setting this up, I'll have x minus z equals to negative 4, knowing that x equals to negative 5. So this is now negative 5 minus z equals to negative 4. From here, we'll go ahead and add 5 to both sides of your equation. Simplifying this after your additive inverses cancel out, we'll be bringing down negative z, which equals to 1. Yes, the negative sign is ugly. Yes, I will fix it. There we have it. Now, in solving for z, divide both sides by negative 1. Your negatives will cancel out to give you z equals to negative 1. Go ahead and hold on to that. So now we know 2 out of the 3 variables we were searching for. So let's take that first equation in the original system and solve for our final variable. The final variable that we don't know yet, okay? And that final variable is y. So what we'll do is we'll plug in negative 5 for x, minus y, minus 3 times negative 1 for z, which equals to 1. Then we'll simplify on the left side. I'll have negative 5 minus y. Negative 3 times negative 1 is positive 3. This equals to 1. Combining negative 5 and 3 together, you'll get negative 2 minus y equals to 1. From here, we'll be adding 2 to both sides of the equation. Your negative 2 and positive 2 will cancel out as its sum is 0. So you'll bring down negative y, which equals to 3. You want to solve for a positive y, right? So you're going to divide both sides by negative 1. Dividing both sides by negative 1 gives you a result of negative 3 for y. Go ahead and hold on to that. Writing our answer as an ordered triple, you'll have an x value of negative 5, a y value of negative 3, and a z value of negative 1. Red, box it. Just like that, party people. There you go. Yeah? There you go. That's what we do here. We solve problems. Let's move on. Here I would like to remind you guys that you can set up a paid online tutorial today with FBT. Fort Bend Tutoring provides online tutorials, and you can get a personalized one-on-one tutorial with me, Mr. Whitt. That's right, me and you, solving math problems, getting our learn on That's what we do. Thank you very much. Go ahead and check that out by checking out our website, fortbendtutoring.com. There you go. Seek that out. And moving on. From here, we have problem number 4. That's right. We're at problem number 4 now, and we'll be using the elimination method. Once again, I begin the elimination process by identifying terms that will be easy for me to eliminate. So that means I'm comparing all of the X terms, the Y terms, the Z terms, and I'm listening to my lazy voice. That's right. I'm trying to find out which of these variables would be the easiest to eliminate. All right, so I think I'm going to be going with the X's. And the first pair of equations I'll be utilizing to eliminate the variable X is the first and the third. So let's set that up, shall we? Our first equation is 2x plus 6y minus 4z equals to 8, whereas the third equation is negative 2x minus 6y plus 5z equals negative 3. Setting that up, people, what we'll end up doing is being able to cancel out not only the x's, but also the y's. Look at there. This gives us a result of z equals to 5. Yeah. So who knew that just that fast we would be able to find out, we would be able to identify one of the values of our variables. So we now know that z equals 5. Go ahead and hold on to that, okay? Protect it with your life. All right, that being the case, we're going to continue the process. I'll next be eliminating the variable x in the first and second equations. So let's set that up. So setting this up, I'm using the first and second equations this time. I'm bringing down the 2x plus 6y minus 4z equals to 8. And I'll also bring down the 3x plus 10y minus 7z equals 12, just like this, okay? So I told you the purpose of setting up this original system was to eliminate the x's, but we got a little bonus in that, right? We were able to eliminate the x's and the y's, but my initial goal still stands, and that is for me to come up with two smaller equations, okay, that have the x variable eliminated. So that's why I'm going to continue with this system right here, where I'll be multiplying the first equation by negative 3. All right, and I'll multiply the second equation by positive 2. Once again, the goal is to get opposites out of your x terms. So by doing this, by getting these arrows popping in a few seconds here, I'll end up with a negative 6x and a positive 6x. That will allow me to eliminate them. Okay, so we're going to get our arrows popping just like this and distribute these scalars times each of the terms in their respective equations to end up with x terms that are additive inverses, aka opposites. So with that, we'll have the following system now. You'll have negative 6x minus 18y plus 12z equals negative 24. The second equation will be positive 6x plus 20y minus 14z equals to 24. Amen, amen. After having this set up here, we know that our x's will be eliminated. Combining our terms, you'll have 2y minus 2z equals 0. And don't forget that we already know that z equals to 5. So the next step then is to plug in 5 in for z and solve for y. So I'll have 2y minus 2 times 5. This equals 0. You'll bring down the 2y minus 10. That equals to 0 still. Go ahead and add 10 to both sides of your equation, where you'll see your 10s will cancel out, bringing down 2y equals 10, and then dividing both sides by 2. 2's are canceling out here. You'll have y equals to 5. So hold on to that y. Knowing that z is 5, knowing that y is 5, we can now plug these two values into any of the original equations. Now, I don't really dive too much into which equation to use. Most of the time, I just plug it into the first one unless it looks really stupid, okay? So the first equation is fine. It's not going to hurt anybody, right? We'll have 2x plus 6y minus 4z equals 8, and I'll be plugging in 5 for y, and 5 for z. We have 2x plus 6 times 5 minus 4 times 5, and this equals 8. Let's go ahead and multiply and simplifying these equation. You'll have 2x plus 30 minus 20 equals 8. Simplifying here, we'll have 2x plus 10. This equals to 8, and now I'll be subtracting 10 to both sides of the equation, right? The 10s will cancel out as they are additive inverses. Bringing down 2x, this equals to negative 2. We'll be dividing both sides by 2 now, and then simplifying. My 2's cancel out, and I have x equals to negative 1. Put a red circle around that, because this is what we're holding on to as we write our final solution as an ordered triple, that is negative 1, 5, and 5. In other words, our x value is negative 1, our y value is 5, our z value is 5 as well. Red, box it. Just like that, people. And that was problem number 4. Let's continue. Here we have problem number 5, and our method will be the elimination method. We have a system of equations, 3 equations with 3 variables, and we'll be solving for these. So I want to identify a variable that is that looks attractive. Yeah, looks attractive. A variable that doesn't look like it's going to be too much of an issue to eliminate. Right? I'm trying to go with the line of least resistance here. That's what I'm looking for. And what's screaming out to me is the variable y. Yeah, y wants to be eliminated. See those small numbers? Yeah, it has to go. So I'll be setting up a system utilizing the first 2 equations first. I'm going to set up the first 2 equations. I'll be bringing down the 3x plus 2y plus 4z equals to 11. You hate the plus sign, so do I. You're not alone. Then the second equation is 2x minus y plus 3z. This equals to 4. And yes, we will be eliminating the y variable by multiplying the second equation. Oh, you got it. By 2. So we'll be multiplying the second equation by 2. That's what we're going to do here. And then get our arrows popping. That's right. Distributing the 2 here, we'll rewrite the system as 3x plus 2y plus 4z equals to 11. And you'll have 4x minus 2y plus 6z equals to 8. Now we have things set up. Your 2 y's will cancel out. We'll be bringing down 7x plus 10z equals 19. And we want to hold on to this equation. So this is an equation we want to keep in mind. The next thing we'll do is we're going to take the second and third equation and once again eliminate the y variable. So I'll have 2x minus y plus 3z. This equals to 4, whereas the next equation, which is the third equation from the original system, is 5x minus 3y plus 5z. This equals negative 1. Using our scalars here, we will be multiplying the first equation by negative 3. The reason for this is because the least common multiple between this negative y term and the negative 3y term is 3y. Okay, and so I want to make the first y a positive 3y to offset that negative 3y in the second equation in this current system. Go ahead and get those arrows popping, and you'll end up with the following system. You'll have negative 6x plus 3y minus 9z, which equals to negative 12. In the second equation, you'll have 5x minus 3y plus 5z equals to negative 1. So notice that second equation from the system here did not change, as we only needed to get additive inverses, aka opposites, by simply multiplying the first equation by negative 3. All right, so now we have opposites on the y terms. That's what we wanted, because now they cancel out. We're bringing down negative x minus 4z equals negative 13. And we will be holding on to this equation. That's right. Keep this one in mind. Utilizing these two equations, that's 7x plus 10z equals 19, as well as our negative x minus 4z equals negative 13, we want to eliminate one of these variables here. So let's choose the x variable in order to eliminate. Why? Because the LCM is 7x, whereas the other one would be 20z, right? So I always go with the smallest LCM when possible. This means I'll be multiplying the entire second equation here by 7. All right. This gives me the following system. We'll have 7x plus 10z equals 19, and negative 7x minus 28z equals negative 91. Now that we have this set up, let's use our elimination properties here. Our x terms will cancel out, and we'll be bringing down negative 18z equals negative 72. So now we'll be dividing both sides by negative 18, and now your negative 18s will cancel out and simplify to give you z equals to positive 4. So now we know that z equals to positive 4. So now that we know that z equals to 4, we can plug this into one of the equations that just contain two variables. For instance, we can use the 7x plus 10z equals 19. So let's use that. We have 7x plus 10z equals 19. Replacing z with 4, you'll have 7x plus 10 times 4 equals 19. Then you'll have 7x plus 40 equals 19. And then subtracting 40 to both sides of the equation, like so. We know that our 40s will cancel out, and you'll have 7x equals to negative 21. So now that we have this, go ahead and divide both sides by 7. Your 7's will cancel out, and simplifying, you'll end up with x being equal to negative 3. Another value to hold on to. So now with this information of knowing x and z values, we can plug those values into one of the original equations. So the one that looks like it's going to cause me the least amount of trouble is the first equation out of the original system. And that means I'm referring to this 3x plus 2y plus 4z equals to 11 value. And now what we'll do is plug in the fact that we know what the x and z terms are. So we know that x equals to negative 3. And we also know that z equals to positive 4. And we'll be using those two values to solve for y. Simplifying, you'll need to multiply 3 times negative 3 as well as 4 times 4. And this equals to negative 9 plus 2y plus 16 equals to 11. Combining your like terms on the left side of the equation, you'll have 7 plus 2y equals 11. Then subtracting 7 to both sides of your equation, the 7's will cancel out. You'll be bringing down 2y, which equals to positive 4, then dividing both sides by 2. Dividing both sides by 2, and then simplifying, you'll have y equals to positive 2. Hold on to that. And your ordered triple will be negative 3, 2, and 4. X represents negative 3. Y represents the value of 2, and Z represents the value of 4. Red, box it. Just like that, guys. All right, let's move along to problem number 6, where we have a word problem for you. In our word problem, it says a movie theater charges $8 for adults, $4.50 for children, and $6 for senior citizens. One day, the theater sold 405 tickets and collected $2,320 in receipts. There were twice as many children's tickets sold as adult tickets. How many adults, children, and senior citizens went to the theater that day? All right. Setting up our variables, we'll assign the variable x to the adults that attended the theater that day. We'll assign the variable y for the number of children that attended the theater that day. And we'll say that z will represent the number of seniors that attended the theater that day. Looking at our system of equations, the first equation will be the variable x plus y plus z equals to 405, representing the total number of tickets sold for that day. The second equation reflects the amount of money earned that day, as we have $8 times the number of adults $4.50 times the number of children, and $6 for the number of seniors that attended the theater. And that's set equal to the $2,320 that was earned. Finally, the last equation refers to the fact that there were twice as many children tickets sold as adults. That means that in order for the adults number to equal the number of children, we would have to double that amount. That's why you write the equation as 2x, 2 times the number of adults that attended the theater that day, set equal to the number of children, because the children's amount is twice as many as the adults. So now we have our system set up. And the first thing I want to do is get rid of that decimal in the second equation. That is really bothering me. So what I'll be doing is I'll be multiplying each and every term in the second equation by 2. Doing so, I'll be showing that I'll have a scalar of 2 multiplying times the entire equation, and you know we have to get our arrows popping. So I'm going to be distributing the 2 to each and every term within the equation to create an equivalent equation, which will not change the answer to this system of equations. So rewriting it, I have my brace here, and I'll show that the first equation is x plus y plus z equals to 405. And I'll show that the second equation is now 16x plus 9y plus 6z equals 4,640, as well as our last and final equation, which is 2x equals y. When it comes to the third equation, I'm going to go ahead and subtract y to both sides in order to get it into the same format as the other 2 equations. On the right side of the equal sign, the y's will cancel out and you'll end up with the following system. Notice that we now have our equivalent system of equations. Everything is in the same format, meaning that all equations are set equal to a constant. And now we can focus on the elimination method. So what I'm going to do is I'm going to take the first 2 equations and I'm going to eliminate the z variable. Why? Because the third equation doesn't have a z variable. So that means that I'll be able to pair up the result with the third equation. So let's see what happens as I eliminate the z from the first 2 equations. We'll have x plus y plus z equals 405. And then we'll have 16x plus 9y plus 12z, this equals to 4,640. What I'll be doing next is I'll be multiplying the entire first equation by negative 12. Multiplying by the scalar of negative 12 will create additive inverses, aka opposites, on my z terms. This then gives us negative 12x minus 12y minus 12z equals negative 4,860. All right. And then bringing down the second equation, we'll have 16x plus 9y plus 12z equals 4,640. Now that I have everything set up, we can go ahead and use our elimination method and cancel out our additive inverses on the z's. So our z's are definitely going to cancel out, and we'll be bringing down 4x minus 3y equals negative 220. All right. And we want to hold on to this equation right here. It'll be this equation as well as the 2x minus y equals 0 that we'll be using to isolate one of the variables. So now at this stage in the process, we have our 2 equations that we were focusing on, the 2x minus y equals 0, as well as the 4x minus 3y equals negative 220, and we will eliminate one of the variables. I'm thinking that I'm going to go with eliminating the x term. So that involves me multiplying the top equation by negative 2. Now, for those of you that were honing in on the y variable, you could have very well had canceled out the y. There's nothing wrong with doing that. But I have a tendency of listening to my own personal lazy voice, and it was telling me that x is going to be better for me. So that's what I went with. You could have chosen to eliminate the y's, and that would have been just fine, people. So rewriting the first equation, I'll now have negative 4x plus 2y equals 0, whereas the second equation here in the system will remain the same. That being the case, we have our setup and our x terms will now cancel out. This gives me negative y equals to negative 220. From here, we'll divide both sides by negative 1. Simplifying, you'll have y equals to 220. And yes, this equal sign is getting on my nerves. A lot better. We have a value for y now. 220 tickets, and remember the variable y represented the number of children that attended the theater that day. Since we originally had the equation 2x equals to y, then we can replace y with the value of 220. So 2x must be equal to 220. Dividing both sides by 2 and then simplifying, we find that the number of adults that attended was 110, holding on to that value of x. Utilizing the first equation from our original system, which was x plus y plus z equals to 405, and then plugging in our values of x, which is 110, plus our value for y, which is 220, plus z, we'll be able to solve for the number of seniors that attended the theater that day. Going ahead and combining our terms on the left side, you'll add 110 to 220 to get 330, plus z will equal to 405. Subtracting 330 to both sides of our equation, Lexo. The 330s will cancel out. We'll bring down z, which equals to 75. And this tells us our number of seniors that attended the theater. Answering our original question, we now know that the number of adults that attended the theater was 110, whereas the number of children was 220, and finally the number of seniors was 75. These values add to the sum of 405 tickets that were sold at the theater that day. Adding 110 tickets plus 220 tickets plus 75 tickets gives you your total of 405, therefore verifying that our solution is correct. And that completes example 6. Red box it. Just like that, guys. We have our answer, our solution to problem number 6. Look at that. Well, all right, ladies and gentlemen, that is going to do it for solving a system of equations with 3 variables with your boy, Mr. Whitt. That's me. How you doing? And I'll be reminding you guys to donate if you can. Also to subscribe to the YouTube channel Fort Bend Tutoring, and like the video and comment below. And don't forget to let me know whether or not you like the new format with us having the screen displayed instead of having the camera over the iPad like we used to over all of the hundreds of videos we've had in the past. Let me know if this is an improvement for you, and let me know if everything worked out all right. Peace.
Thanks for watching. We appreciate you hanging out with Fort Bend Tutoring. Like the video, comment, and subscribe. Hit up our website, tutoringmath.net, and set up a private tutorial with me and FBT. Oh yeah, baby.